Howdy, stargazers, and welcome to this episode of Star Trails. My name is Drew, and I'll be your guide to the night sky for the period of July the 19th to August the 1st. This week, we're exploring a side of astronomy that most backyard observers never experience. My guest, Hap Griffin, has built a radio telescope capable of detecting the faint radio glow of hydrogen spread throughout our galaxy. Using little more than recycled parts and some off-the-shelf hardware, he's recreating one of the landmark experiments that revealed the Milky Way's spiral structure. The best part? You don't need to spend a lot of money to do it. Later in the show, we'll take a look at what you can expect to see in the night sky in the coming weeks. Whether you're tuning in from the backyard or the balcony, I'm glad you're here. So grab a comfortable spot under the night sky and let's get started. Hap Griffin is one of those people whose curiosity seems to have no limits. He's an accomplished astrophotographer, having been published in magazines like Sky and Telescope. His astro photos have literally been carried to the moon as part of the Moon Arc project. He's photographed countless NASA launches and received the Clyde Tombaugh Award for his contributions to amateur astronomy. He's even discovered an asteroid. But lately, Hap has turned his attention to something many backyard astronomers have never even considered: radio astronomy. Using less than $100 worth of equipment, he's recreating one of the landmark experiments in 20th century astronomy, the same experiment that helped reveal the spiral structure of our own Milky Way. I recently sat down with Hap to learn how it all works and why it's much more approachable than you might imagine. I'm here with Hap Griffin. Hap, thanks for taking the time to be on the show today. I sure appreciate it.
Well, I love doing this for you guys.
Now, you've spent years as a visual astronomer, but more recently you've turned your attention to radio astronomy. What drew you into that side of the hobby?
Well, of course, I've always been interested in astronomy and really got into photographic astronomy back in the late 90s. But my background has always been in radio and radio engineering, broadcast engineering. So radio astronomy was the perfect way to mix these two interests. It's just a natural for someone who has a background in radio to be able to take advantage of that to study another aspect of astronomy that obviously just visual astronomers can't get to.
While most of us are spending our nights collecting light through a telescope, your radio telescope is doing something very different. At a high level, can you explain what's happening?
Well, it turns out that when we're doing visual astronomy, we're working through the visible light spectrum. And if you look at the entire spectrum of electromagnetic radiation, it goes all the way from very low frequency radio waves down in the AM radio that you might have in your car, that kind of frequency, up through X-rays and gamma rays and all these sorts of things that are very much higher in frequency than what we can see. And it turns out that the visual range that we can see, that you always see as a spectrum between red and violet, is just a tiny narrow window that is in the pretty much the middle of the spectrum that is. But radio waves open up the entire spectrum of emissions from astronomical objects that by limiting yourself just to the visual frequency range, you're totally going to miss out on. Of course, you can do radio astronomy in the daytime. Night, day doesn't matter. Generally, weather doesn't matter. So you can do radio astronomy pretty much 365.
You know, one advantage that immediately comes to mind is just weather. Here in the southeast where we are, we spend a lot of time waiting for clear skies, and you really don't have that problem.
You might wind up with one clear night a month during these periods of time here. And even though the wintertime is cold, it's also the clearest, and so you have to make do with that when you're dealing with visual astronomy. But for radio astronomy, doesn't matter the time of year because the objects are going to, whatever's in the sky you can pick up, and weather doesn't really make a difference.
So let's talk about what you are picking up out there. When I arrived today, your dish was pointed almost directly toward the center of the Milky Way. What exactly is your telescope measuring, and what does that tell us about the galaxy?
Yeah, it turns out that one of the easier ways of getting started with radio astronomy is by picking up what I call the heartbeat of the Milky Way. It turns out that there's a physical process that is really astounding to think about. We live in a galaxy that is composed of stars and gas and dust, and most of that gas is hydrogen. That's the most abundant element in the universe. Once in every 10 million years, for an individual atom, there'll be a spontaneous flip of the electron spin axis. And what'll happen is it'll give off a photon of energy, and you can calculate the frequency and the wavelength of that energy. And it turns out it falls right in the radio spectrum at 1420 plus some little bit of megahertz. And you would think that, well, if a single atom only does it every 10 million years, you'd never have anything to look at. But it turns out that when we're looking at arms of the Milky Way galaxy, you're looking at hydrogen clouds that are hundreds or thousands of light years across. And within that cloud, there's, a gazillion atoms of hydrogen. And at any one time, there are lots of atoms that are firing off and doing that spontaneous flip. And it makes a radio signal a continuous radio signal that you can actually pick up on a receiver.
So once you've detected that hydrogen signal, how do you go from a simple radio measurement to actually mapping the structure of the Milky Way?
There was some conjecture back in the mid part of the 20th century that we lived in a spiral galaxy, because we can see other galaxies, and a lot of them are spirals. But we couldn't visualize it by just looking at the Milky Way itself, because we're inside of it, and you're looking along the equator of the Milky Way, and you really can't see those arms. And so it was proposed that we use the detection of this hydrogen emission that we just spoke about to actually measure what shape the shape and size the Milky Way was, because radio waves can travel through all of that dust that blocks our visual sighting. And sure enough, back in the 1950s, a couple of scientists did this same experiment. They put together an antenna and a receiver, and they started mapping out these arms of the galaxy in the emissions of hydrogen. And sure enough, it came out to show that we do live in a spiral galaxy. So what I'm doing is basically replicating the work that they did back in the 1950s to determine what the shape of our galaxy is. And sure enough, making these observations on my own and creating a spreadsheet that analyzes the data that comes from it, the spiral shape of the galaxy just falls out of the math. And it's just fascinating to me.
So you're making a visualization of the shape of the galaxy itself. You're collecting measurements, plotting them on a graph, and somehow the structure of the galaxy emerges from that data. That's a fascinating way to do astronomy.
These radio waves, like I said, this one particular is at 21 centimeters in length, and the antenna is only a few times that in diameter, and so you don't really have a lot of resolution. The antenna I'm using right now is about 6 degrees, so if you could imagine dividing the sky up into 6-degree pixels, that's basically what I'm looking at. So you're looking at a fairly big patch of sky at one time. But the receiver takes and plots out the signal level versus the frequency, and it just saves those numbers in a file, and I can take those numbers, that file, and import it into a spreadsheet that I've built, and it draws out the graphs and gives you information on how fast the object is either coming towards us or away by calculating the Doppler effect and all that sort of thing. So that's how you actually can visualize what you're seeing when the numbers are coming from a really relatively low resolution source.
Another piece of the puzzle is the Doppler effect. The hydrogen line shifts slightly depending on whether that gas is moving towards us or away from us. Is that how you're able to reconstruct the galaxy's structure?
Well, go back just to the concept of Doppler shift to start with. If you think about if you stood beside a train track and you see a train coming towards you and it blows its whistle, you hear a high-pitched whistle as it's coming towards you, but as it passes you, the pitch of that whistle drops off. The whistle hasn't changed. It's just the speed in relation to you, the velocity in relation to you has changed. Same thing happens with electromagnetic radiation. Objects that are coming towards us at a significant fraction of the speed of light tend to have their spectrums shifted towards the blue end of the spectrum. In other words, the wavelengths become compressed together and the frequency rises up. Something that's going away from us has the opposite effect. The wavelengths get stretched out. The pitch of the sound, if you will, gets lower in frequency, and so that's called Doppler effect. We know, for instance, that the hydrogen emission is an exact frequency at 1420 point some odd megahertz, and but when we see that same emission either risen up in frequency or lowered down in frequency, we can take and do some math to it and figure out how fast that object is going away from us or coming towards us, or the other way around, us towards it or away from it. Depending on where you aim your antenna along the equator of the Milky Way, if you aim your antenna towards the core of the Milky Way, for instance, we're just in orbit around the core, and the emission that you see from the core of the galaxy doesn't shift very much from where it's supposed to be at 1420 megahertz. But if we start looking off to the side, 10, 20, 30, 40 degrees east of the core of the Milky Way, along the equator of the Milky Way, what we see is signals that are being shifted lower and higher in frequency depending on what time of day it is, what time of year it is, that sort of thing. So we can tell how fast we're moving in relation to that cloud of gas that we're looking at, either towards it or away from it. And you can build a model. Once you do a systematic study of the whole Milky Way, you can put it all together in a model, knowing which parts are coming towards you and which parts are going away from you. And that's where the shape of the galaxy, in terms of the various arms of the galaxy and the rotation, comes out of these equations.
Yeah, from the graphs you've shown me, the spiral structure really is visible in the data. And by the way, I'll make some of this data available on the show website so folks can see what you're working on. But I mean, it's just amazing that you're doing this with equipment that is actually surprisingly simple.
One of the most mysterious questions in all of astronomy, what type of galaxy and what's the shape of the galaxy that we're in, whether it's a spiral or an irregular galaxy or one of a number of different types, and how fast we're moving around it, things like that. All of these really deep questions can be solved with $100 worth of hardware. It really is funny. I mean, you can build an antenna, a workable radio telescope antenna, out of a small Wi-Fi dish.
Okay.
That's like 3 feet in diameter. And I got one out of a scrap pile. And you can buy the actual receiver that you use is what they call a software-defined receiver, an SDR. And it's a little USB thing that plugs into the USB jack on the side of a computer. Costs about $40 from Amazon. And you need to boost up the signal from that small antenna before you go to the receiver. And Amazon sells what's called a low noise amplifier specifically for this frequency. And it's also about $40. So, about $80 worth of hardware and an antenna made out of scrap and some free software. You can detect the heartbeat of the universe yourself. If you go through the math and everything, it pretty much answers those fundamental questions about where we are in the galaxy and what the galaxy's shaped like and all of that.
I'll include links to these items in the show notes because I think that's one of the most remarkable things about this technique. An astrophotography setup can cost thousands or even tens of thousands of dollars or more, but yet for around $80, someone can start measuring the structure of our own galaxy.
That's right. Even cheaper than that is there's areas of radio astronomy that anybody who is an amateur radio operator probably already has this gear. For instance, the planet Jupiter has immense storms on its surface and interactions with one of its inner moons that gives off a signal at one of the shortwave frequencies around 20 megahertz. And so any radio amateur who has a receiver and an antenna for that part of the spectrum can aim their antenna at the eastern horizon. When Jupiter comes up above the horizon, they can hear it at that frequency. They can hear the noise that it generates. So you're listening in on some physical calamity that's going on out in Jupiter's atmosphere with just a receiver that you might listen to any shortwave broadcast with.
For anyone out there listening and thinking, hey, I'd like to try this, where would you recommend someone begin?
YouTube is your friend when it comes to experimenting with radio astronomy. Just type in hydrogen line astronomy or amateur radio astronomy, and there's hundreds and hundreds of videos produced by people like me that show you how to do it and what you need to do it and types of things that you'll find and all of that. So the internet is a great resource, particularly YouTube.
Tell us about your observatory. What does the equipment look like?
Right now, I'm running a 2.4 meter diameter parabolic dish. It's and a homemade feed horn for it that I built in my workshop, and it's set up at my observatory, which is about 40 or 50 miles from where I live here. And the reason I've got it up there is because when there's nobody there, it's radio quiet. In other words, it's exceedingly sensitive. And so it picks up any interference, like say if somebody else is there and turns on a computer or something like that, it causes noise in the receiver. And so I don't want to have it here at my house. For another thing, I live in an HOA, and I don't think they would take too kindly for a big satellite dish out in the backyard. But anyway, it's a 2.4 meter diameter, what people used to call a satellite dish. It's actually a microwave dish that I got from scrap. And it's mounted on a concrete pedestal that I built. I've got a way of remotely tying into that system. Even though it's 40 miles from here, I can tie into it from my computer at the house and operate it here at the house, which is when I usually do it when there's nobody else up there at the observatory site.
Since you're working with incredibly weak radio signals, I imagine interference becomes a real concern. What are the biggest challenges in dealing with that?
There can be some of the strongest the strongest sources of interference are astronomical in origin itself. In other words, the sun. The sun puts off a tremendous amount of radio noise. And when the Earth turns and moves my antenna across the sun, or the sun appears to move across my antenna, it basically swamps the receiver. And so it's useless when the sun is within a few degrees of my antenna. But otherwise, anybody that has a computer on within a couple of 100 feet or things like that generate what we call broadband or wideband radio noise, that affects it too. But so that's why, like I say, I have it remoted from here at the house, and I operate the system when there's nobody else around up there.
So now that you've mapped the Milky Way, what's your next challenge?
I want to be able to detect other galaxies. In other words, we have one relatively next door to us that's almost our twin called the Andromeda Galaxy. It's about 2.5 million light years away, and I want to try to increase the sensitivity of the system such that I can actually see the hydrogen in that galaxy. And that's going to be a little bit of a stretch, but I think I can do it with the equipment that I have.
I look forward to seeing that. I was talking with Dr. Enrique Lopez Rodriguez a few months ago. He's a friend of the show. And when I mentioned your work, he said, that's not amateur radio astronomy. That's radio astronomy. That's science. And, that validation has to be rewarding.
It is. And of course, I'm not discovering anything new. I'm essentially replicating science that was done 50 years or 60 years ago, which is fine with me. But what's fun is doing it with my own gear, most of it homemade, with spreadsheets that I wrote the software for, and being able to come up with the same conclusions that they did, 50 years ago with this little bit of very simple off-the-shelf hardware.
Hap, thanks so much for taking us behind the scenes of your radio observatory. It's been fascinating, and thanks for joining us on Star Trails.
My pleasure, always.
I can't thank Hap enough for that interview, and if his voice sounds familiar, it may be because you heard him back in our Star Party episode. Interestingly, when I arrived for that interview, Hap had his dish pointed toward the heart of the Milky Way. On his computer screen, a distinct bump stood out at that hydrogen line, a clear sign we were looking through dense clouds of hydrogen gas near the galactic center. By the time we finished talking, around 45 minutes later, the Earth had turned, the Milky Way had moved, and that once prominent peak had nearly disappeared. And nothing about the equipment had changed, the galaxy had simply moved on. And that was probably the best demonstration of radio astronomy I could have asked for. It's remarkable to think that something as simple as a small dish antenna, a USB receiver, and a graph can reveal the structure of our galaxy. Sometimes the universe doesn't need spectacular images to tell its story. Sometimes all it takes is a small indication on a graph and knowing what you're looking at. Now, let's step outside and see what's happening in the night sky over the next few weeks. The moon will dominate the early part of our observing period. On July the 21st, it reaches first quarter, making this one of the best times of the month to explore the lunar surface through binoculars or a telescope. The long shadows along the terminator, that's the line dividing lunar day from lunar night, bring craters and mountain ranges into dramatic relief. As the week progresses, the moon will continue to brighten, becoming a waxing gibbous before reaching the full buck moon on July 29th. Unfortunately, that bright moonlight will wash out many of the fainter deep sky objects for a few nights around full phase, but it's still a beautiful sight in its own right. The buck moon is named for the time of year when male deer are growing a fresh set of antlers. These new antlers, still covered in soft velvet, are growing at an astonishing rate during the height of summer. If you've got a telescope, here's a fun challenge for some of the evenings early this week. Just off brilliant Vega in the constellation Lyra is Epsilon Lyrae, better known as the double-double. To the naked eye, it looks like a single faint star. Binoculars reveal two stars, and under good seeing, a telescope at around 100 power will split each of those stars into another pair. You're actually looking at a 4-star system. This is a classic summertime test of your telescope's optics and the steadiness of the atmosphere. Planet-wise, Venus continues to shine brilliantly low in the western sky after sunset. It's the unmistakable evening star. Saturn is becoming a real treat in the late evening and early morning hours. Rising before midnight, it's climbing higher into the sky each night, giving us steadily improving views of its rings as they begin opening back up after appearing nearly edge-on from last year. Meanwhile, Jupiter has disappeared into the sun's glare as it approaches solar conjunction on July the 29th. It'll return to the morning sky in the weeks ahead. If you're looking beyond the planets, don't overlook two of summer's showpiece deep sky objects. The Great Hercules Cluster, also known as M13, is nearly overhead during the evening. Just to the south in Sagittarius, the Lagoon Nebula, or M8, is another rewarding target through binoculars or any small telescope. Even under modest skies, both objects are well worth your time. And finally, we begin entering meteor shower season. The southern Delta Aquarids and the Alpha Capricornids both peak on the nights of July the 30th and the 31st. The Delta Aquarids typically produce around 20 meteors per hour under dark skies, while the Alpha Capricornids are known for fewer meteors but an occasional spectacular fireball. This year, though, the nearly full moon will make conditions less than ideal. You still have a chance to catch the brighter meteors, but the moonlight will hide many of the fainter ones. If you head outside after midnight and let your eyes adjust, you may still be rewarded. That's going to do it for this week. If tonight's episode sparked your curiosity or maybe gave you something new to think about the next time you look up, I'd be honored if you shared Star Trails with someone who might enjoy the journey. You can always find the latest episodes, show notes, and extras at startrails.show. And if you'd like to help support the show, there's also a little Buy Me a Coffee link on the site. It genuinely helps keep these stories coming. Be sure to follow Star Trails on Blue Sky and YouTube. Links are in the show notes. Until we meet again beneath the stars, clear skies, everyone.